So we now look at case 2 of circular motion, where omega, which is the angular velocity, is not a constant. We have already talked about the situation where omega is a constant, and that was an introduction to circular motion. The summary of it is that at every point in time, when an object traverses a circular trajectory, it defines a position vector r of t, which is radially outward. It has a magnitude r and the direction cos theta I plus sin theta j, where cos theta I plus sin theta j is the direction of the unit vector r roof, and r roof is also radially out. We define another unit vector theta roof tangential to the circular trajectory, and that is negative sin theta I plus cos theta j. All these derivations are in the previous video. And now there is a linear displacement that occurs along the circumference of the circle. That is, at another point in time, the object will move from this position 1 to another position 2. So there is a linear displacement along the circumference. That is delta r. If we can recall from the previous video, delta r at an infinitesimal time is represented by this linear distance, but it is pointed in the direction theta roof, so it is a vector. And it defines an angle delta theta at the center of the circle. And theta is called angular displacement. So delta r, which is a vector, is equal to delta theta multiplied by the r in the direction theta roof. So the radius of the circle is a factor that converts an angular parameter to a linear parameter. The derivative of the angular displacement also reflects as a derivative of the linear displacement. So the derivative of the linear displacement, which is a linear velocity, is equal to the derivative of the angular displacement times the radius of the circle, theta roof. We define another term, omega, called angular velocity, as the theta dt. So then the whole linear velocity is equal to omega, which is a function of time, times the radius of the circle in the direction theta roof. So every circular motion has a linear velocity tangential to the circular path. And that's what we are familiar with. Then the derivative of the linear velocity gives us a linear acceleration. And we look at case 1 where omega is a constant. So dv dt, if omega is a constant, and also given that r is a constant, we would first have a notion that then the linear acceleration will be 0, because the derivative of a constant is 0. But in this case, it's a no, because the unit vector theta roof is not a constant. At a point in the trajectory, it points in this direction. Within another moment, it will point in an entirely different direction. So theta roof keeps on changing along the circumference of a circle. That gives it the linear acceleration. So though omega is a constant, dv dt is not a constant. In fact, it gives us negative omega square r, where another omega that we got over here was due to theta roof. Theta roof is negative sine theta I plus cos theta j. So its derivative will give us another omega stemming from the theta dt. That is why this is omega squared r in the direction negative r roof. So the linear acceleration given a constant omega points in the direction negative r roof towards the center of the circle. The last parameter is omega is 2 pi over t. 2 pi is the angular displacement for a complete revolution, and capital T is a period. And 1 over t is defined as a frequency. The frequency is the number of revolutions per the period. So if within every period it undergoes 1 revolution, then the frequency is 1 revolution per period. That's why the explicit formula is 1 out of t. It is a reciprocal of each other. And that is also to tell us that the angular velocity is directly proportional to f. The more you revolve around the circle, the more your angular velocity is, because you create more angular displacement within a short time. Let's now look at case 2. For this, omega of t is not a constant, it is a variable. The language of mathematics, the language of physics is mathematics. And if you're able to interpret the mathematics properly, you can read the physics into it. Stay tuned. So we are looking at case 2, where there is a varying omega of t. The angular velocity is now not a constant. And the only equation in town is that the linear velocity v of t is equal to omega of t. Omega is now a function of time times r in the direction theta rho. So what that means is that the object is not moving with a constant angular velocity. It doesn't traverse equal angles in equal times anymore. So at one time, it will be taking 1 omega. At another time, it will be speeding up. Then keeping on speeding up. See? Or slowing down. So what happens is omega is not a constant. And the linear velocity would never be a constant also, because they are directly proportional. The derivative of the linear velocity, you would recall, is equal to a linear acceleration. And this time around, it is going to be equal to, this is not a constant, this too is not a constant. The only constant here is the radius of the circle. So the derivative of this quantity is going to be the derivative of this and the derivative of this one. So this is going to be r, which is a constant out, maintain omega of t, differentiate the theta roof, and you're going to get the theta roof dt plus, so r multiplies the whole quantity. Now it is time to maintain theta roof. Differentiating the omega of t dt. We are able to do this from the chain rule. The constant r is factorized. Maintain omega t, differentiate the theta roof, which is a function of time, plus maintain theta roof, differentiate the omega of t. This quantity, omega of t, the theta roof dt, we can recall that to be the centripetal acceleration. So let us expand this. Now omega of t, let me put that here, omega of t, the theta roof dt is equal to negative omega of t squared times r in the direction r roof. That is a centripetal acceleration. We just did that now. That was the case when omega was a constant. And even though here omega is not a constant, it is the same quantity at that point in time. Let's prove this. What is theta roof? Theta roof is negative sine theta I plus cos theta j. So the derivative of theta roof, that is theta roof, the theta roof dt is equal to, derivative of sine theta is negative cos theta I, derivative of cos theta is negative sine theta j. The derivative of negative sine theta is negative cos theta then we have the derivative of the inside to be d theta dt before the I minus sine theta. Then we take the derivative of the theta, which is d theta dt j. And if we factorize the theta dt out as well as the negative out, we are going to get negative d theta dt into bracket cos theta I plus sine theta j. But then the theta dt is omega. So negative omega cos theta I plus sine theta j. So the derivative of theta rho is negative omega, which is a function of time, into bracket cos theta I plus sine theta j. But cos theta I plus sine theta j is r rho. And given that there is one omega here already, that omega will multiply this omega, and you are getting omega squared. Then times the radius of the circle. And that radius is because of this r outside. So the bottom line is omega of t times the theta rho dt will give you negative omega squared r in the direction r rho. So this is equal to r multiplying the whole of this quantity is negative omega squared, which is a function of time, times r rho. So omega of t d theta rho dt is negative omega squared r rho. And we can prove the theta rho of dt is equal to that negative omega, and this is r rho, and this omega multiplies this omega, we are getting omega squared times this r rho there, and then plus the omega t dt the direction theta rho. That is a linear acceleration. So if we push the radius into the bracket, we are getting negative omega squared, which is a function of time, times r, the direction r rho, plus the omega dt is a new quantity. So this time round, the angular velocity also changes with time, and we give it a name, angular acceleration. And we give it a symbol alpha. So alpha times r in the direction theta rho. And this is the dynamics when an object moves around a circle with a non-constant omega. It turns out that the linear acceleration component has two parts. One is called the centripetal acceleration, which we already have discussed. Centripetal acceleration. Centripetal means center seeking. Center seeking, it seeks the center, centripetal. Negative omega square r is called centripetal acceleration, and that is a prerequisite for circular motion. Even if omega is a constant, this value must be there before the object can traverse a circular trajectory. And now, when the object speeds up, in other words, when you whirl the object in such a way that it doesn't move with a constant omega, but it speeds up, you exert a force tangential to the circle at every moment. So while it is moving with 1 omega at this point in time, you speed it up at this point in time, then you speed it up, continue to speed it up, you give it an angular acceleration that we call alpha. which is the omega dt. It only appears when omega is not a constant. Otherwise, this derivative will be 0. And that was case 1. But in case 2, alpha is not a 0. And multiplying that by r in the direction theta roof, we call it a tangential acceleration. The tangential acceleration is the angular acceleration, which is alpha, multiplied by r, which is also a linear parameter. So this linear acceleration has 2 parts. One is centripetal. I mean, if this is a circular trajectory and an object is here, there is a centripetal acceleration like that. And if you speed the object up, it will get another linear acceleration vector in the direction theta roof. This is a negative r roof. That is opposite r roof, defining r roof to be radially outward. The centripetal acceleration is like so. If you speed the object up, it will have another linear acceleration component tangential to the circle. So the net acceleration of the object will be pointing at one oblique direction at any point in time. In our next episode, we are discussing Newton's laws of motion. And the second law deals with forces. And whenever you have a force, there is an acceleration. So there is a force exerted on this object at every point on this trajectory. That is why it is getting 2 components of the acceleration. And even if it has one component, the centripetal acceleration, there is still a force towards the center of the circle. And if you are the one producing that force, if you speed it up, you have a linear acceleration component tangential to the circle and a centripetal one. So for a variable omega, the 3 angular parameters are angular displacement, that is theta, angular velocity, that is omega, and now angular acceleration, which is alpha. And alpha multiplied by r, we call that tangential acceleration. One of the linear accelerations tangential to the circle. One is centripetal, which is toward the center of the circle. So for circular motion, this is a necessity. It's a prerequisite. In other words, if this isn't there, the object cannot traverse a circular trajectory. So even when omega is a constant, you still have this. But for a variable omega, then alpha will set in, giving it a new acceleration called tangential, and the overall will be at an oblique direction. So if you are the one stuck, say, on a circular trajectory, it could be a chain, then the chain is speeding up. If the chain is speeding up, it means there is a net force towards this direction. And to be able to cling to the chain to save your life, you need to apply a force equal in magnitude but opposite in direction to that net force, which will be the mass of u times this whole acceleration. So the magnitude of this acceleration, A, is going to be equal to one component radial and one component tangential. So it will be equal to the square root of this parameter squared plus this parameter squared, square root of negative omega squared r at that point in time, squared plus alpha r squared. That will be the magnitude of the net acceleration. So multiply by the mass, which will be the next episode, force. You are getting the force at which you have to hold the chain to cling yourself to it, so you save your life. And the direction is in the direction of this oblique direction of both theta roof and negative r roof. Given the net acceleration for every circular motion to be negative omega, which is now a variable, squared r, the direction negative r roof, plus alpha, which is the angular acceleration, times r in the direction theta roof. So there is one centripetal component and one tangential component. For the tangential, we have alpha, which is the square theta dt, dt squared, or the omega dt, also called the angular acceleration. So we have theta, which is angular displacement, omega, angular velocity, and when omega changes, we have alpha, which is angular acceleration. The motion parameters out of these three, which can be converted to linear parameters. So in actual sense, the motion itself is linear, but the analogy of the linear is angular, and you can convert from one to another. If you have the angular parameter, you can convert to linear, and vice versa. So for linear motion, theta is x in one dimension, or y. Omega is v, vx, or vy. Alpha is a, ax, or ay. So this is linear, and this is angular. The angular parameters first appear in circular motion, where the linear displacement or linear position becomes angular displacement or angular position, where linear velocity now becomes angular velocity, and linear acceleration becomes angular acceleration. And the beauty is that you can convert from one to another. And in the special case of circular motion, if you multiply the angular parameters by simply r, the radius of the circle, you get the linear parameters. So theta r is x, omega r is v, alpha r is a. The analogy of the motion equations, the kinematic equations, for the angular parameters are, so now theta of t, the angular displacement of the object as a function of time, is equal to the initial angular position plus omega naught, that is the initial angular velocity, times time, plus half alpha t squared. And the second equation is the derivative of this one. And the derivative of this is omega, which is a function of t, is equal to omega naught. This one will be 0, but this will be omega naught plus alpha t. And the derivative of omega will give you only alpha, which is a constant. So these kinematic equations as angular parameters are established when alpha is a constant. So the last equation is omega squared is equal to omega naught squared plus 2 alpha delta theta, where delta theta is angular displacement. These kinematic equations are not really actual motion. The actual motion is linear, the linear ones that we already know. But it is good we know the angular parameters too, so we can easily convert to linear parameters in circular motion. Our next episode is a discussion on Newton's equations or Newton's laws of motion. And these are the rudiments for classical mechanics. Please subscribe, share, click on the notification bell, comment, and like. Stay tuned for more interesting stuff.